hard. Okay, so today, I just want to say there's no, hold on, let me connect my pencil. So, as you know, there's no class on Monday, so Monday, right? Because it's Memorial Day, I believe. So what I'm gonna do is the next quiz, next week will probably be posted after section on Wednesday, and the quiz will be on integrals, yeah, because that's pretty much the big thing we have right now, or I'm going to start going over today. So any questions? Here. Okay. So, okay, let's get started. So integrals. So for now, let f be bounded on AB. So for now, we're only going to consider bounded functions on intervals of numbers. Yeah, like strict numbers. So like we don't have like to infinity. Yeah. And we let S be an AB. So this is just notation. We denote capital M of Fs to be the sup of f of x, where x ranges over all elements in S. Yeah, and little m Fs to be infimum of f of x, where x runs through all of S. So we're gonna start, if you remember from Math 2a, like the integral was like a limit of Riemann sums, right? And if you did Math 2a, you did like left sum approximation, right sum approximation, and basically you took like points, like you divided up your interval AB, right? So that's pretty much what we'll do. So we'll say a partition of AB is finitely ordered, so it's ordered and it's finite, right? So you can have you cannot have infinitely many points. Ordered subset P, right? So we normally write the first term is our starting point. So A is T naught less than T1 all the way so up to Tn, and the last point is B, right? So an example, like on 1, 2, I can partition up 1, 2 in, I don't know, 1.1, 1.5, 1.7, and 2. So that's a partition, right? So T naught is 1, T1 is 1.1, T2 is 1.5, and I guess T5 is 2. Okay, so we denote the upper, I don't know how to pronounce this name, Darboux. I believe it's Darboux. So Darboux sum to be UFP. So no, it depends on the partition, right? So for every partition, you have a upper Darboux sum of F with respect to P, right? P is a partition, is UFP. So this is like in math, not math 2a, math 2b, like the rectangles, right? So F T K minus 1 TK, right? So let me TK, and then times TK minus TK minus 1. So again, you could think of this as, we choose a height, and this is these are this parenthesis, yeah, multiplying by the difference. This is the width. Yeah, so an example would be if my partition was, the one above. So let me just, 1, 1.1, 1.5, 1.7, and let's say 2, right? Ugh, that was bad. Then what is the upper Darboux sum? Well, let's draw a function, right? So let's, I don't know, up to here, and then it goes down. Yeah, so you see here, what is the upper Darboux sum? So here, again, this is, let me just write T0, T1, T2. I guess they start at T0, so sorry. Yeah, sorry, it's T0. They start at 0. And then this is T3 and this is T4. Yeah, so what's the width, right? The width is T1 minus T0, right? And that is exactly what you get if you plug in K equals 1, right? If you plug in K equals 1, the width is T1 minus T0. And what's the height? Well, recall what M is. M is the sup of F on the interval, on whatever interval you're in, right? So it's the supremum of F on this interval. So I drew it that is increasing. So the sup is like something like this, right? So this is my rectangle. And then I go to the next one, right? I take the width, and in this case, the sup, since it's increasing, it's this, yeah? And then I go here, next one, right? And then here, I guess the sup is what? The sup is some here, yeah? The sup is like right there. And then and then we sort of, it's the area, right? So it's the sum of these. So we add them up. And so that's the upper Darboux sum. So recall if you view integral, I mean, obviously I didn't define what it is, but like as area under curve, you sort of see the upper Darboux sum is always an upper estimate, right? So UFP is upper, I guess overestimate, right? Because on each interval, we're taking the supremum, right? Capital M is a supremum. So I'm taking the largest value of F over like the interval. So of course I'm gonna have like, it's gonna be, there are some terms right here, right? That I, overcount. Okay. And then similarly, we define the lower, so lower Darboux sum to be, same thing, but for the height of the rectangle is the infimum. So times tk minus 1. Okay. So one thing to note is you have a bound on each one, right? So for UF of P, this is what? Again, let me just rewrite it. It's capital M of F tk minus 1 tk times tk minus 1. Now I could bound this by just saying, forget I'm taking sup over tk minus 1 at tk, right? So let's forget that. Let's just take sup over F on all of AB, right? Since F is bounded, this is some number, right? Here, I'm taking sup over a bigger set. Remember, like the TK is partition AB, right? So obviously AB is the biggest set. So here, right, it's certainly bigger than if I just replace it with the sup over the whole set. And this thing no longer has a K in it, right? So I can pull it out. Now, what is this? If you write it out, all the terms cancel, but the first one and last one, right? So if you write out like if K equals 1, it's T1 minus T0. k equals 2, it's t2 minus t1. The t1s go cancel, right? If I plug in k equals 3, I get t3 minus t2. The t2s cancel, so on and so forth, right? So you see the thing, you'll see that the only thing that remains is minus t0, and at the end it's tn minus 1. The tn minus 1 goes away. So you see that this is just, equal to m f a b of times tn minus t0. But what's tn minus t0? Tn's your last point, it's b. T0 is a, right? Is your starting point, right? So this is just m f a b times b minus a, right? So there's always a bound on this upper thing. And similarly, you can check that the lower is bounded below by the infimum of f on the whole interval ab times b minus a. Okay, is everyone clear so far? So far we have this. So let me just write f a b times b minus a is smaller than the lower Darboux sum. And it's clear that the lower Darboux sum is smaller than the upper Darboux sum with the same partition, right? The p with p is the same, because on one of them you take sup, the other one you're taking inf, and this is smaller than m f a b, right? Times. So it isn't intuitively obvious that taking different partitions, is it still true L is less than U? It is, but yeah, you will have to. We'll prove that it's 0. So okay, so now we define the upper Darboux integral to be u of f. So note here, if I write u of f with no p, that's the upper Darboux integral, yeah, of f over ab. So what is it? It's the infimum of all the u of f p's. So infimum of what? What am I taking infimum over? Over all partitions. Partition of AB, right? So I had like one partition here, right? So if I take another partition, if I get something smaller, I take that one, right? And then so on and so forth. I mean, there's infinitely many partitions. And then the lower Darboux integral, L of f over AB, is given by the supremum of L of f, right? And the supremum over our partitions. So remember, L of f is always smaller than in the actual area under the curve, and U of f is always bigger, right? Because we take sup and inf. So if you sort of think of, recall when you learn limits, how do you approximate limit? You take the lim sup and lim inf, right? And then if they're equal, then it's the limit, right? If they're not, then it's not, right? So you could sort of think of like U of f as like approximating integral from above, and L of f as approximating integral from below, kind of like lim inf lim sup. So UF sort of acts like lim sup, LF sort of acts like lim inf, right? And turns out, let me just write turns out, this is the case. So note this is not obvious, right? Because here this is obvious because it's the same partition, right? So for example, it could be like the infimum was actually attained for like partition P2, and here the supremum was attained for partition like P1, and you don't know how different partitions relate, right? So okay, so again, define Remember, just like how if lim sup equals lim inf, it's the limit, right? So f integrable on AB if and only if L of f is U of f, right? And L of f equals U of f. And then we denote the integral to be like this, yeah. So again, these two are just shorthand for this, yeah. It's just notation. Okay, so one thing to note is we have if f is bounded on AB and if PQ are partitions such that of AB, you know, AB, such that P is contained in Q. So what does it mean for a partition to be contained in the area? A partition is a set of points, right? Ordered points. So to be contained means all the points of P are points of Q, yeah? So what does that mean then? L of FP is, so you get a better approximation, right? Because remember, we're taking sup of the L of F's. So getting a better partition should be, you know, get you closer to the integral, right? And U of FQ less than equal to U of FP. So let me just show this by picture. So if you go back here, let's say this was my partition P, right? And let's say P has to be contained in Q, so Q must contain all the points here. So let's add in, I don't know, let's add in this, a point here, yeah? So what will my rectangle become? My rectangle will become, you know, something like this, right? The rectangle from here all the way to here. But then the sup on from here to here is like this point, right? So you sort of see we took out this overestimate, right? So my upper sum should be smaller when I, you know, because I'm getting closer and closer to my actual integral, right? Because the actual integral was the infimum of all the uppers. So by taking more and more partitions, your overestimates become less and less, right? And by taking more and more partitions, right here, your underestimates should get more and more. I mean, less and less. So your thing becomes bigger, right? So you see here when I added more points, you know, I get smaller, right? And here when I add more points, I get bigger because it was an underestimate. Okay, so is everyone good so far? Okay, so we have a theorem. That's pretty useful. It says a bounded function f on AB is integrable if and only if for all epsilon bigger than 0, there exists partition P on AB such that U of FP minus L of FP is less than epsilon. So why is this nice? It's because this, I mean, if your goal was to show us integrable, I mean, one way would be to calculate this, right? But you know, how are you gonna calculate all partitions? There's infinitely many partitions, right? So what this theorem says is you just need to find one partition where the difference between the upper and lower is less than epsilon. Yeah, and the way you sort of see this is, let me just try to sort of convince you, right? It's just the definition of sup and inf, right? So in English, let me just say in English first, if U of F was, you know, is infimum remember, if you have an infimum, there's a sequence of points going to it, right? In this case, there's a sequence of partitions such that I'm, going to the infimum, right? So I could find a partition like epsilon over 2 away from U of F, and then I could find another partition that's epsilon over 2 away from L of F, combine them, and then, they'll be less than epsilon, right? So let me just sort of tell you how the argument works. So again, right, U of F was infimum, because it's pretty important, this property. So choose partition and like this refinement property. Partition P1 such that U of F, why did I put parenthesis? U of F P1 is, less than epsilon over 2 away from U of F. Yeah. And then L of F was supremum, right? So choose partition, so it need not be the same partition, right? The ones that are close. So choose partition P2 such that L of F P2 is less than epsilon over 2 away from L of F, right? And so I'm sort of going one way, yeah? And so I'm sort of, showing this way. And then the other way, hopefully, if that's true, it's 0, right? Because epsilon was arbitrary. But this way, right? If you look at it, okay, so we're sort of almost done here, right? We sort of want to say, okay, U of F P1, U of F, right? So we're sort of squished in between, right? So remember, if a L of F is the correct thing, so if it's integrable, then how does this compare? This is one particular partition. It's an underestimate, right? So it should be smaller than the actual integral, right? If it's integrable, L of F is equal to U of F. If integrable, right? So we're assuming it's integrable. So L of F is U of F. And U of F, for this partition, is an overestimate, right? Okay, well, this is epsilon over 2 away. This is epsilon over 2 away. So it is true that these are epsilon away, but the question wants 1p, right? We have a p1 and a p2. So how do you fix it? Well, there's something called refinement. This is something you should know for sure. Refinement. So basically, combine all points, right? Combine all points. So define P to be all points in P1 and P2. So we certainly have this, right? If I add in more, so let me just do an example so everyone's clear. If, P1 is the partition given by 1, 1.3, 1.5, 2, P2 is, I'm really bad at making up numbers, 1, 1.2, 1.7, 1.9, 2. Then P is the combination of them. So 1, 1.2, 1.3, 1.5, 1.7, 1.9, 2. Yeah. So now the nice thing is, what's the nice thing? If using the thing I just said, right here, right? If I have a subset, I only get more and more accurate, right? So here, you sort of see that from here, since it's a subset of P, I have L of FP2 is less than or equal to L of FP, which is less than or still less than or equal to the actual integral. right? Because this is an underestimate. I'm taking infimums, and we assume this was equal. And then L of U of FP, U of FP1, right? That's P1, yeah. But again, these were epsilon over 2 away. So this is in between, right? So this is clearly epsilon over 2 away. And this was epsilon over 2 away. So this is even less. So this is epsilon over 2 away, at least. Then the difference is epsilon away, right? So hopefully that's clear, right? So difference. I mean, you can write it out using triangle inequality or whatever, but this is just, hopefully it's obvious. So difference is less than epsilon. Right, so you can always make it one partition by taking like refinements. And refinements only make your thing more accurate, right? So, okay. Any questions so far? Okay. So there's another theorem which is something similar. So again, you use whichever one you like. It's pretty much equivalent. F bounded. So F integrable if and only if for all. Oh, right. I'll define this later. But for epsilon greater than 0, delta greater than 0, such that mesh of P is less than delta, then U of FP minus L of FP is less than epsilon. So this is more useful to show it's not integrable, right? For all partitions P of AB. So you see here, this is not that great to show it's integrable because you need to check it for all partitions, right? The top thing, you just need to check for one partition. So you see here, I'll define what mesh is. So, but you see here, it's only good to, to show them something is not integrable because you just need one partition such that this is less than delta and, that's not less. So mesh of a partition P. So let's say P is, A is T naught. Again, this is just convention. All the way to Tn is B, right? The mesh of P is just the maximum of the differences. So, right, for K equals 1 to N, yeah? So the maximum length of the mini intervals that you partition. Okay, is everyone clear so far? Okay. So hopefully, so this is not really the thing you learn in 2B, right? Because you don't, in 2B, you don't take the sup and the inf, right? You hopefully you either learn left rectangle, right rectangle, or midpoint rule. Yeah. So so that one is just Riemann sum. And it's something similar. So F bounded on AB, and P is partition of AB. Right, again, by convention, I'm using, this notation for the partition. Then the Riemann sum is given by sum K equals 1 to N F of XK TK minus 1. So it's something similar, right? XK is in TK minus 1 TK. So before, remember, we took the sup, right? So Riemann sum is just pick any point in the interval and evaluate F. So if we go back to the here we took the sup, but here it's just say pick any point, go here, and then that's your height. So, and you could choose any point. So if you chose the left one, if you chose like 1, if you choose the left one every time, it'll be called the left Riemann sum. If you choose the middle one every time, it's called midpoint rule. And if you choose the right one every time, there's right Riemann sum. But the idea is when you do more and more partitions, your intervals get closer and closer, right? At some point, your intervals are so small, like it doesn't really matter what point you pick. So, because if you think of dividing an interval into infinitely many pieces, your lines, just look like points, right? Unless you get a microscope. So, okay. So again, we say that f is integrable, Riemann integrable, if there exists r greater than 0 such that for all epsilon greater than 0, there exists delta such that s minus r is less than epsilon. For every Riemann sum, and any partition P with, mesh P less than delta. So it's sort of like the equivalent of like the Darboux thing. And then there's a theorem that says Darboux is Riemann, pretty much. So whichever one you like, use whichever one you like. The R ends up being, UFP, LFP, right? If F is integrable. The Darboux agrees with Riemann. So, okay, let's start doing questions. Is everyone clear so far on the theory? Range of our quiz. You mean like the topic or like the points? Is that at 10 points? Are you talking about today's quiz or next week's quiz? Well, next week is just integrals. So, yeah, it's what I'm going over now, and we'll be going over next Wednesday, because we don't have class on Monday. So, good. And today, this week is Taylor's theorem, right? So, okay, let's try to find the, whether is f of x equal to x for x in Q and 0 x not in Q. Is this integrable? Right? So, again, I need to find, some. So let me ask, what do you all think? So let's try to calculate what L of let P be partition. Yeah. Oh, sorry. On 0 to B. Yeah. Sorry. I needed to give you an interval. So let P be partition of 0 to B. So, again, 0 less than or equal to T0 less than T1. Oh, no, sorry. Equal to D0 less than T1 less than T2 less than Tn equals B. What can you tell me about the lower sum, like the lower Darboux sum? LFP is, again, let me just write it out, to N MF T on the interval TK minus 1 times TK minus 1. What can you all tell me about the lower sum? Anyone? Again, what is this m, little m? It's the infimum of my function f on the interval TK minus 1. So what's the infimum here? Yeah, it's zero, right? I mean, any interval, there's an irrational, right? So the infinite is zero. So the lower sum is just zero. And in fact, uh, since this is true for all partitions, right? My partition was arbitrary. You get L of f is zero actually, even though we probably don't even need that. But so you see here, U of fp has some positive things in it, right? Like the soup is just the largest number in the interval, right? So like, because if tk from tk minus 1 to tk, if we're taking soup, the biggest one is tk, right? And if tk was rational, then it's just the value tk. If tk was irrational, well, there's a sequence of rationals going to tk, so your soup is still tk. So you sort of see here, we sort of expect, the the this not to be true, right? So what we're going to do is we are going to use where was this? Yeah, so this one. So if we expect it's not going to be integrable, let's use this. So let's assume it is integrable, and let's choose an epsilon. Then there's some delta, and then we derive a contradiction. Yeah. So assume f is integrable. Is integrable. Then I'm just gonna let epsilon be a fourth. Yeah. In this case, 1/4 works. So I chose a fourth. So then let epsilon equal a fourth. Then the theorem says there exists delta such that for all partitions P with mesh P less than delta, we have what? Yeah, mesh P less than delta, U of Fp minus L of Fp is less than epsilon, right? I don't know why I put parenthesis here. U of Fp minus L of Fp is less than epsilon. In other words, sorry, less than a fourth, right? Epsilon is a fourth. I mean, we sort of showed L of Fp 0, right? So basically, U of Fp is less than 1/4. Okay. So what we're going to do is you always want to change this to something, rational points. So let's take partition P given by, I don't know, let me think. Given by like, oh, it might be scaled. I don't like the B. In my notes I assume B was 1, but okay, let's just work it out. So given by let's take our length of our interval to be 1 over, so so there exists, does everyone agree there exists n such that 1 over n is less than delta? Yeah. So I need, this one means the largest length of my intervals is less than delta. So what I'm gonna do is I'm just gonna make my intervals 1 over n. And what I'm gonna do is I'm gonna say, okay, here I'm gonna divide up my interval from 0 to b to be 0, 1 over n, 2 over n, 3 over n, all the way to bn over n. So everything has length, sort of 1 over n, except that last term. But for simplicity, is it okay if we assume b was 1? Because I really don't want to deal with irrationals. So let's just change this problem to 1. Yeah, just to get nice numbers. It's really it doesn't change the argument, but just to make things nice, let's make it n over n. So here, so 0 to 1. Yeah. So here, what we're going to do is we're going to say, okay, let's calculate it, right? U of FP. So if you did it with B, there's like some factor of B. So again, M of F, and then in my case, it's, what is my interval? It's I over N to I minus 1 over N, right? Times, and what is the length of my intervals? It's 1 over N, right? So yeah, and this I equals 1 to N. Yeah, I mean, this was supposed to be I over N minus I minus 1 over N, right? The difference between the two intervals, which is 1 over N. So what is the sup here? Can anyone tell me? The supremum is just this, right? It's just the largest point. So I over N times 1 over N. And this is what? This is 1 over N squared, sum I equals 1 to N of I. And what is the sum? Hopefully you all know. It's a famous sum. This is N times N plus 1 over 2. Yeah. And what is this? So this thing is, if I factor out an N, I get times N squared 1 plus 1 over N over 2. And this is bigger than a half, right? But so we get a contradiction here because I was supposed to be smaller than a fourth, and yet I'm bigger than a half. So, right, and remember, to be integrable for any partition P with mesh P less than delta, my mesh P is 1 over N, and I chose 1 over N to be less than delta. So all I need to do was find one partition with the length of my interval is less than delta, such that the difference is not less than a fourth, right? So this is one example. Okay, any questions so far? So it's going to be hard to compute U of F. That's the thing. I actually feel the book assumed it was an easy task, but it's actually not. So you sort of see here, what you're going to see is U of FP. If you take N to infinity, it's going to go to a half, right? So if I take my N bigger and bigger, but U of F is smaller than U of FP for any P, right? So U of F, all I know is that it's smaller than or equal to a half. I mean, unless you could show it's like bigger than or equal to a half, then yeah, but I'm not sure how you would do that. Are you clear? Yeah, I mean, computing U of F might be a pain. I think the book asks you to, but I feel it's very hard to do. So yeah, okay. So let's actually try to compute integrals. Yeah. So something we know is integrable. Upper and lower Darboux sum. Darboux integral for x cubed. Yeah. On. Okay, let me just do it with B this time. I really don't like it, but let's do it with B. So we're going to have factors of B, but okay. So let's compute U of PF. So how you're going to do this is you're going to choose a partition that's good enough. Now, good enough, it requires, so the first thing you try is, the 1 over n's. So in this case, let's partition it by B over n. So 2B over n all the way to Bn over n. Yeah, so we have n terms, right? So my TK is like KB over n. So again, so what is my sum? So sum k equals 1 to n, m, so this is my f of x, m of f on, let me just think what it is. Tk is kb over n and k minus 1b over n, right? That's tk minus 1 times, what's the length of my intervals? It's b over n, yeah? Hopefully that's clear. The length of these intervals is b over n. Now, what is the sup? What is the biggest term here? X cubed is increasing, right? So it's just the value of the largest term, which is this one, right? So I get k cubed b cubed over n cubed, because that's the value of my function, times b over n. And so here I get b to the fourth over n to the fourth, which I can factor out, right? I mean, there's no k there, right? I can't factor out the k cubed because my sum is dependent on k. And again, there's a famous formula for this. Just look it up online if you forgot. But it turns out to be n times n plus 1 over 2 squared. So this is what? This is b to the fourth over n to the fourth times n squared times n plus 1 squared over 4. Now, when n goes to infinity, right? So I'm taking partition Pn for every, if you think of my Pn is whatever n is, and I take n to infinity, this thing goes to b to the fourth over 4, right? So I know that since I'm taking infimum, right, and I found partitions going to b to the fourth over 4, my upper sum is, my u of f is less than or equal to b to the fourth over 4, right? I mean, I don't know if it's equal. I mean, a priori, if you integrate x cubed, it's x to the fourth over 4, right? Which is, and if you evaluate b, it's b to the fourth. So it is equal, but we don't know that yet. We just know it's less than or equal to, right? Because we're taking infimum over all partitions. So it could be, right? So here I chose like infinitely many partitions, but there could be infinitely many more, right? So I don't know if those infinitely many more makes my overall integral smaller. Okay, but in this case, we don't need that. So in this case, let's compute L of P of F for the same partition, right? Same partition, right? So this is what? This is k equals 1 to n again, little m of f on the interval, again, kb over n, k minus 1b over n, times, again, my intervals are of this length. And same argument, right? What's the smallest value? This k. The smallest value is this one, right? So it's k minus 1 cubed over n cubed b cubed times b over n. And similarly, b to the fourth over n to the fourth. So, this is just shifted by 1, right? So before it was n times n plus 1 over 2 squared. So now it's going to be, instead of n, it's n minus 1 times n over 2 squared, right? And this thing goes to where? This thing similarly goes to b to the fourth over 4 when n goes to infinity, right? So my partitions like p1, p2, if n is the index, it goes to b to the fourth over 4. So I found a sequence of partitions going to b to the fourth over 4, but L of P of F is the supremum, right? So L of F is the supremum over all partitions, right? So this is only bigger than or equal to b to the fourth over 4. But then you are done, right? Because L of F is smaller than or equal to U of F. We said that U of F was smaller than or equal to b over 4, b to the fourth over 4. And this one's bigger than or equal to b to the fourth over 4. From this, you get equality, right? So And I mean, it's obvious, right? If you integrate this, I mean, we all know how to integrate, but if we do it illegally, this is b to the fourth over 4, right? So you should expect to get this. But yeah, so is everyone good with this? You know, hopefully we sort of understand. It's the same thing as lim sup lim inf, right? I mean, lim sup lim inf is like a pain to compute. And so similarly, the upper and lower is a pain to compute. But that is the definition. So